Hello there, ladies and gentlemen. We are going to go over Unit 2. I wanted to record this video as a quick review presentation for you before you take your Unit 2 test. So we are going to start with Objective 1, which talked about the evolution of Earth's atmosphere and how that evolution of our atmosphere kind of co-evolved with life on Earth. Another part of that objective is looking at the relationship between the four main Earth's sphere. We have the hydrosphere, the atmosphere, biosphere, and the geosphere. So we are going to start with a review of the formation of our atmosphere. So you should remember that the Earth formed about 4.6 billion years ago. The early Earth did not have the same atmosphere as we are experiencing today because of the vast volcanic activity on the planet. So a lot of gases that were present in that time in our atmosphere were carbon dioxide. We had no oxygen, but we did have small amounts of other gases like methane and ammonia. Moving on, along with those gases that were released with the volcanic activity, we had water vapor that was released into the atmosphere. Eventually, that water vapor condensed to form the oceans. So at that point, the water being present, water is a great solvent, meaning that it will dissolve a lot of substances, including gases. So one of the gases that it dissolved was ammonia, which led to creating ammonia compounds and nitrogen-containing substances. And then the nitrogen ended up being stored in the atmosphere because it is so unreactive, and that nitrogen is still there today. About 2.7 billion years ago, we see the evolution of first photosynthesizing organisms. So we had our plants, algae, our cyanobacteria that was now going through the process of photosynthesis. And if you remember from the notes, we have a couple of things that are needed for the process of photosynthesis. We do need carbon dioxide, which plants would take originally from the ocean water. We do need the presence of water, and that reaction will yield glucose, which is stored within the plant's structure, and then oxygen is being released as a byproduct of photosynthesis. Now we know that that happened around that time because we have a record of that in banded iron formations. So banded iron formations are actually stored in the Proterozoic rocks, which will vary in age from about 1.8 to 2.7 billion years old. They are composed of alternating layers of iron-rich mineral, in particular magnetite, and then silica minerals. They form kind of like a layers and layers of alternating colors, where you have that red, rusty looking iron and then lighter colored silica minerals. So early on in the Earth's primitive atmosphere, there was really no oxygen that was available in the atmosphere. So those rocks that were iron rich were actually weathered away, and that should sound familiar, right? Where rocks are going through the process of weathering by being broken down by elements like wind or water. And those particles were actually carried away, so they were eroded into the oceans. Well, at that point, because there was no oxygen in the atmosphere, that iron was not rusty at all. it was a pure iron that was, eroded or weathered away from those early rocks. As that iron was carried into the ocean, at that point we discovered that we had early photosynthesis taking place. So we have those primitive blue-green algae that was beginning to take action and evolve in the near surface waters, right? Because they would be found near the surface because they need the sunlight to go through the process of photosynthesis. As the algae would produce that oxygen as a waste product of photosynthesis, the free oxygen would now be available in that water and would actually form or bond with those iron ions to form magnetite and iron oxide. That's pretty much what it means, is that those iron particles would rust in the water, which in order for rust to take place, we need to have oxygen, free oxygen, being available for that reaction to take place. Okay, so those rusty particles, if you will, settled down in those layers of what we call today banded iron formations. We do not see any rocks like that forming today because the conditions were very different in the ancient oceans as opposed to the oceans that we have today. Okay, so moving on to our history of atmosphere. Now that we have this oxygen being available in the atmosphere because we have those early photosynthesizing organisms producing, and that excess oxygen is being released to both waters and then into the atmosphere, now we begin to see the evolution of animals, right? Because they needed that oxygen for respiration, and then they would release carbon dioxide as a product of that respiration. So the cycle began of that photosynthesis and respiration. Okay, moving on to, fast forward to today's atmosphere. It is very different than the one that was found in the early Earth. We have 78% composition affiliated with nitrogen. We have about 21% of oxygen, and then the 1% are trace gases like carbon dioxide, argon, methane, water vapor, etc. Now we changed the composition of the atmosphere because of the amount of fossil fuels that we are currently burning as a society on a global scale. Okay, so we are changing that composition because currently, we are at somewhere around 415 parts per million in terms of CO2 within our atmosphere, which is very different than what it was even 200 years ago. Okay. So this is a good diagram showing you the progression of life as it evolved on our planet. So we started off with, this really early stages of our solar system where we have the sun formation, and then we have our Earth forming after that, because remember, our planet formed by the process of accretion or accumulation of materials in that early solar system formation. Then we had our moon that was being created as a result of a collision with another planetary object. We had our first prokaryotes, cells without nuclei evolving, and then photosynthesis took place. Okay, once photosynthesis took place, that entire cycle of life have changed, because now we had that free oxygen available for life to evolve. So we started with eukaryotes and then bacteria, and then as life evolved, our animals and plants have changed over time. Now remember, we need to look at our Earth as a system. It's a system of interconnected parts, and we have 4 main spheres when we talk about the Earth's being a system, right? Those parts depend on one another, they're interconnected, and we can start with our atmosphere. The atmosphere is the layer of gas that's surrounding our planet. We have the biosphere, which will include all of the living things, including plants, animals, and all the other organisms. We have the geosphere, which will include the rocky part of our planet, like the crust, mantle, and inner and outer cores. And then the hydrosphere. The hydrosphere is going to be your water available in the oceans, in lakes, rivers, groundwater, and water vapor. Oftentimes you will also hear about cryosphere. Cryosphere is part of the hydrosphere, and it includes the frozen water. So, for example, the ice caps. And here's another image which will show you that those parts within the Earth system are all connected, and that we have ability to influence and change the system. If you remember playing the Jenga game, you hopefully remember that it doesn't matter which block you pulled away from the tower, you could have a devastating impact on the entire tower. So by us releasing greenhouse gases into the atmosphere, right, we're changing the atmosphere, we're changing the physical climate of the planet, okay? If we go through the process of combustion, right, and it could be naturally occurring forest fires, we have a lot of aerosols that are being released into the atmosphere that have, an impact on the climate that's long-term. We can change the chemistry of our atmosphere by burning fossil fuels, right? Or burning different chemicals that are not healthy for our planet. And then we can change ecosystems. For example, we can go through the process of deforestation when we remove vast amounts of forested areas and turn them into agricultural land. So that will change the balance of photosynthesis and the exchange of carbon and the storage of carbon in the biomass. So I do want to go through an example of how there are interactions within different spheres or between different spheres, looking at volcanism. So we can start by saying that before the eruption, you can have a excellent, diverse ecosystem, right? That ecosystem will have a lot of different plants and animals living then. Then we can have the eruption itself, right? And as you could imagine, the eruption will have an impact on the land and the population that's surrounding that volcano. So for example, when we look at the atmosphere, right, what kind of impact can a volcanic eruption have on an atmosphere? Well, we released a lot of different gases. There's a lot of dust that's being released into the atmosphere, and then also volcanic ash, right? That will change the atmosphere. And if you remember, we talked about how, volcanic ash can actually lead to cooling of our climate because it blocks off a lot of the sunlight that's supposed to be reaching the surface. we can think about what kind of impact will that eruption have on a biosphere, right? We can have loss of life, and it could be human life, it could be plant life, it could be animals that live in that immediate area surrounding the volcano. What kind of changes can we see in a hydrosphere, right? We have all that dust and ash that, that fall into the ocean. Those could also act as a condensation nuclei. Okay. And what condensation nuclei is a particle that's present in the atmosphere that actually water can condense around, forming water droplets, right? So after a massive eruption, we can actually see an increase in rainfall because we have that condensation nuclei that are there to start those water droplets with forming. And then, of course, we have the change in the geosphere itself, right? I mean, we just had a massive volcanic eruption. We have new rocks that are forming. We have the layer of dust that's settling now, forming sedimentary rocks. You can have your different rock formations that are ejected from the volcano in addition to your lava flows. So I hope that gave you an idea of kind of what we're seeing and how different events can have different effects on the different spheres within our Earth system. And here's another picture that you can hopefully take a look at for a little bit of time. If you need to pause that video, you can go ahead and do that. You have the 4 spheres listed in the circles, and then the different changes that act between those 4 spheres. So hopefully you can notice that there are changes and there are effects and causes of changes, and they're all interconnected. So entire system works because all of the parts of the system work. If you have a failure of one of the systems or one of the spheres, the entire system may fail. Think about it as your human body, right? You have all your organs that work in sync together to make sure that you're healthy. If you have liver failure, if you have heart failure, if you have kidney failure, if you have certain organs failing, chances are that the entire system may fail. Okay, moving on to our objective 2, which talks about the carbon cycle. The first objective talked about the processes of photosynthesis and respiration and how they work together to move that carbon through the different parts of the system. And then the second objective talked about how the carbon can move between the 4 spheres within Earth's system. So we're going to start with photosynthesis, and again, hopefully this is going to be a very quick review because I know you guys are very familiar with this. Okay, so when we talk about photosynthesis, there are a couple of things that we need for photosynthesis. Well, what do we need? We need carbon dioxide. Okay. We also need water. And in the presence of light, right, because you do need to have a light source, what you are going to end up with, what's produced, it's glucose. Let me erase that. Okay, CH. Okay, we have glucose and we have our oxygen that's being produced as a byproduct. It's like a waste product for photosynthesis. So what we're going to do is we're going to write it out. So you have carbon dioxide, right? We have water, and as a product of that reaction we are going to have glucose and oxygen. Okay, and we will need to balance that equation. Again, not something that I need you to do for the purpose of this class, but I don't want to leave it unbalanced. Okay, so this is what we need. This is what we should be able to recognize as the process of photosynthesis. For the purpose of this class, I will not expect you to write down the molecules. Okay, so you do not need to worry about that. You should be able to recognize this. Okay, so make sure you are familiar with this. Okay, so going back to our notes here, talk about cellular respiration. So again, we can go back to my writing here. For respiration, we kind of have the opposite what we had for photosynthesis. So what do we need? Well, we do need oxygen, and we do need glucose. Okay, and then what we are going to produce as we go through respiration is carbon dioxide. Do produce some water, and then ATP. ATP is the energy that we gain by consuming glucose. Okay. And then I'm going to balance that. Right. So again, we have our oxygen that we uptake through breathing, right, through inhaling. We have our glucose, which we gain from our food, right? So we either eat plants or we eat animals that eat plants. We do produce carbon dioxide, water vapor, and ATP, which is the energy that we need. Again, I do not need you to memorize the chemical equation, but I do want you to be able to come up with the word written equation. So hopefully you see that there is a link between photosynthesis and respiration. The equations are flipped. They're exactly opposite. That's why we can have plants and animals living in sync in water, for example, in a lake or pond that doesn't have much in terms of incoming oxygen, because those plants provide the oxygen for the fish and the snails and all the other organisms that live in that pond water. Okay, so moving on, hopefully you can identify and kind of go over the four major parts or contributors to carbon cycle. We just went over photosynthesis and respiration. There's also the process of combustion and decomposition. Now, an image like this, I hope that you can kind of recognize this and be able to identify it. The arrows will show you the direction in which carbon is moving. So, for example, for letter A, we have carbon that's shown as the movement from hydrosphere into the biosphere. So what process would allow carbon to move from hydrosphere into the biosphere? Well, hopefully you can think of one, which would be the photosynthesis of aquatic plants, right? They would take the carbon from the water and store it within the biosphere. Okay. For letter B, carbon that moves from atmosphere and into the biosphere, that could easily be your photosynthesis of land plants. When we talk about carbon moving from biosphere and into the geosphere, we can think about decaying live organisms, or, well, it used to be alive, right? So the carbon is decaying, it's moving from formerly living things and stored into the soil or into the rocks. When we move carbon from geosphere into the atmosphere, well, that's most commonly done by the combustion of fossil fuels. Okay. Oops, let me go back here. Okay, here's another image that looks very similar to the one beforehand, but I wanted to show you both of those. So for letter A, we have carbon movement from biosphere into the hydrosphere. Well, we could see that through the process of respiration of aquatic animals, right? So you can have snails that are going through respiration and they are releasing CO2 into the hydrosphere, into the pond water, for example, that they live in. That could also be true for respiration for plants at night. Remember, plants do go through the process of respiration in the absence of daylight. Again, for letter B, we have carbon moving from atmosphere into the biosphere. That could be your photosynthesis, right, where we remove carbon dioxide from the atmosphere and it is stored in the biosphere. Same thing for letter C, right? The carbon is moved from hydrosphere into the biosphere. That would be due to photosynthesis of aquatic plants. Again, in here, kind of similar from the previous picture, where you have carbon moving from geosphere and being stored into the atmosphere or released into the atmosphere. That could be due to burning of fossil fuels. Okay, moving on to our final objective that talks about Earth's climate. Here we talked about how naturally occurring events or cycles can lead to climate change. We also talked about how human-induced changes can change, or human-induced effects can have changes, long-term changes to the climate. So for naturally occurring climate change, hopefully you remember we talked about a few of the different things here. We started with Milankovitch cycles. Right. Let me see here. We can right, we have 3 Milankovitch cycles that hopefully these will ring a bell. Right? We have the change in tilt. Right? Currently we are at 23.5 degrees, but that tilt is going to vary from, over time, from about 22, and it can go to 24.5 degrees, right? So that tilt is going to change, be affected by that. Right? The second part of the Milankovitch cycles has been the wobble of our planet. Right? So we have our precession. Right? So that's the wobble of our planet. Right? So if you could imagine our planet. So in the first one for the tilt, right, we have our planet, right? The tilt can be, and this is very exaggerated. So if this is the axis and this is the equator, right? So the tilt will change from being tilted a lot to not being tilted as much, right? And again, this is very exaggerated. For the wobble part, what happens is the direction of the Earth's axis is going to change over time. Okay, so over time, the Earth is going to wobble. So over time, this is what happens. And then you may have your new direction of the axis of our planet, right? So currently we are pointing towards Polaris as our North Star. In the future, in about, I want to say 14,000 years from now, we are going to have Vega as our North Star. Okay. The last of the three Milankovitch cycle talks about eccentricity. Okay, and that's pretty much talking about how elongated our orbit is. So if you could imagine our sun being right here, right? Currently, our orbit might be something like this, right? And over time, in the future, and that cycle is about 100,000 years when it takes for the entire cycle to complete, you know, the Earth's orbit might be squished a lot more. Going back, remember that I'm going to go back here. A couple more things we talked about. We talked about plate movements, right? So you have plate tectonics that will allow for the climate to be different as the plates move around the globe. We did discuss the El Nino, La Nina oscillation, also known as ENSO, right? The El Nino Southern Oscillation, and that talked about the ocean surface water changing over time because of the change in prevailing winds. Okay, so if you could imagine, let's see, I'm going to move, I'm going to have Asia on this side of the screen, and then we're going to have South America over here, right, with the Pacific Ocean in here, right? During normal years, we have our prevailing winds blowing in this direction, right? And as the wind blows, it will drag the surface water that's normally pretty warm, right? Because it's a tropical equatorial area, so the surface water is going to be warm. So as the wind blows in this direction, it will allow for that warm water to pool towards Asia, right? Now what happens here then, you have this upwelling of cold, nutrient-rich water off the coast of South America. Now this is beneficial for people that live in South America that depend on fishing for food and income. And then in here in Asia and Australia, what happens with all this warm water sitting there near the coast, you're going to have a lot of evaporation, right? And warm water, warm air is going to hold a lot of water vapor in it. And then eventually that air is going to cool off, form clouds, right? And eventually you're going to have precipitation in here, so a lot of rain, which is beneficial for people growing crops in Asia. So this is your normal year, right? Now during the El Nino year, that oceanic structure looks a little different, right? So again, we look at Asia and South America, right? We have our surface water. What happens is those prevailing winds weaken. So they are no longer blowing as strongly across the ocean water. So they weaken and they will actually kind of stop, right? They will go this way and then they will kind of weaken out. So it will actually create this cycle of wind. Well, that creates a problem because all that warm water near the surface pools across the entire ocean, right? That creates an issue because we have now a lot of evaporation near South America, right? And that's where you will form your storms, right? A lot of precipitation near South America and drought in here, right? So in South America, we have very wet conditions, right? Lack of fish because we no longer have this cool, nutrient-rich water coming to the surface, right? It gets blocked by this warm water, so we have loss of fish, right? And that causes a problem for the populations that depend on fishing. And then the last thing that we talked about was volcanism. And I kind of mentioned it earlier, you know, with the release of dust and ash, right? What that will lead to is blocking of sunlight. So it will actually create cooling effect for the either local climate, or sometimes if the eruption is significant enough, if there's enough of that dust and ash being spewed into the atmosphere, it can have actually a global effect on climate. Now, when we're going to talk about greenhouse effect, we are going to look at how that happens and why is it important to our planet. Because we need to have a greenhouse effect, otherwise we would be in a lot of trouble. We would have conditions similar to the ones found on the moon, where you have a temperature difference between daytime and nighttime of about 400 degrees Fahrenheit. So that would not be very good. So this is our Earth's surface, right? We have our sun, a happy guy, and you know, as the sun is releasing its energy, that energy is coming in towards Earth as a shortwave radiation. Okay, that shortwave radiation has no problem penetrating through the atmosphere. Okay, it's incoming as a shortwave radiation reaching the surface. Now what happens is some of that radiation is bounced back by the cloud coverage, right? So not all the radiation makes it to the Earth, but the ones that do make it through the atmosphere reach the surface. Now, that surface will warm up, and actually what happens at that point, the Earth is re-radiating that energy as a long wave radiation, also known as latent heat. Okay. So that's something that the Earth is re-radiating, sending back into space. Now, it's important for us to realize that we have our greenhouse gases that are in our atmosphere. Okay, we do want them there. We need them in there because we need that blanket around our planet to allow for some of that heat to be stored and kept near the surface. If we didn't have our greenhouse gases, all that latent heat would escape back into space. So we would have, like I said, conditions similar to the ones found on the moon, where you have 400-degree difference between daytime and nighttime. But because we have that blanket of greenhouse gases, for example, carbon dioxide, water vapor, methane, those gases will actually absorb some of this latent heat and then re-radiate it back to us like a nice blanket. Okay, and all of those gases will send back some of that heat to us. And I think I gave you guys example in class. Think about it when you're really cold, when you're sitting on the couch, you know, listening through my notes here. You might get chilly, so you will go and get a blanket or an extra sweatshirt, right? Your sweatshirt is not responsible for producing heat to make you feel warmer. What it does, it actually acts like an insulator, right? So it catches your body's heat and re-radiates it back to you, making you feel warm. So we actually have that greenhouse effect because all those greenhouse gases are actually capturing that energy that the Earth would normally release as latent heat, and then they send it back to us. Now, this is all good for maintaining that mild environment on our planet. However, if you have too much of greenhouse gases, we are now, you know, sending a lot more of that heat back towards our planet, okay, which normally would be released back into space. So we have now a situation where we put a lot of greenhouse gases into the atmosphere. Well, now you may feel as you put 7 sweatshirts on, right? It might be, it might get to the point where it's too warm for you to be comfortable. And that's kind of what we're seeing with having too much of greenhouse gases spewed into the atmosphere, that we will see that warming. So there are some things that people do that influence the climate, right? We can have the changes that we have an impact on the biosphere, the hydrosphere, the atmosphere, and the geosphere. By burning fossil fuels, right, we're changing that environment. You know, we will have effect on biosphere because certain species may not be adapted to living in warmer climates. We can change the hydrosphere because now we have more carbon dioxide available in the atmosphere that acts as carbon dioxide might be put into or absorbed by the oceans, which will create higher acidity levels because CO2, when you mix it with water, it will actually form carbonic acid, which makes it, you know, more of an acidic environment. And some species may not be able to survive in that acidified ocean. You know, we're changing the atmosphere. We're changing the composition of our atmosphere by spewing those extra greenhouse gases. And then we're, of course, changing the geosphere. By warming of our climate, we might lead to melting of permafrost. Permafrost is this permanently frozen soil that has a lot of methane stored within it. And part of the issue why we had that huge warming at the Permian and the end of Permian, if you recall the leaf activity that you have done where we noticed this huge spike in temperatures over a short period of time, scientists believe that happened because there was a large release of methane into the atmosphere. which methane is a much more potent greenhouse gas than CO2. So permafrost will store a lot of that methane within it, and it's fine as long as permafrost is permanently frozen, right? Now, if we warm up the climate, if we allow for that permafrost to melt, that will release the CO2 or the methane into the atmosphere, promoting even further warming. So that's unfortunately something that we will need to face at some point, just as we did at the end of Permian. And that will conclude our notes, our review for Unit 2. I hope you find it helpful. I hope you find it useful. Please let me know if you have any questions. I hope you took notes. I hope you got some better understanding of the material. If you have any questions, let me know, and I will see you in class.